Hello students, welcome to the EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics, University of Delhi. Today we will continue to discuss the Gram-Schmidt theory which we introduced in the previous module. So this is the second part of the Gram-Schmidt theory from the paper Mathematical Physics. So students, let us see what we are going to learn in this module. In this module, you will learn to obtain other eigenvalues and their eigenfunctions. Remember that in the first module, that is in the module before this, you learned that Gram-Schmidt theory tells you that at least one eigenvalue exists. Now, we will learn about other eigenvalues. You will learn to continue to specialize to symmetric kernels, resulting in a host of interesting results from the point of view of physics. When the kernel K of an inhomogeneous integral equation f of x is equal to g of x plus lambda integral a to b kxy fy dy, where gx and the kernel kx are given real functions, lambda is a number, and fx is unknown function which is to be determined but is assumed to be real. The kernel is further assumed to be symmetric. The Hilbert-Schmidt theory gives elegant result for the solution of the equation. We will assume that all the functions gx, k and fx, as I mentioned earlier, are real. In the previous module, we obtained one eigenvalue of the inhomogeneous Fredholm equation. We will now try to obtain the other eigenvalues. Given that the maximum characteristic k1 is equal to 1 by lambda 1 corresponding to the eigenfunction f1 of x must exist, we look for other eigenfunctions. We look for the maximum of the integral I, defined as the two-dimensional integral over dx dy, the limits on both variables from being a to b. Integrand is kxy, the kernel, f of x and f of y. So we have to maximize this integral subject to two constraints. Number one, that the integral f square dx from a to b is equal to 1. And number two, that the integral of fx f1x dx from a to b is equal to 0. That is, f is normalized and f is orthogonal to f1x. We define a kernel k1xy which is equal to the original kernel xy minus the product of the functions f1x, f2y divided by lambda 2. We now look at the integral I2 from a to b over dx dy, the integrand being k1xy fx into fy. We assume that this integral I2 can take positive values and we maximize it like in the previous case, which being the case where this is not true will be treated shortly. We can maximize I2 the same way as we did I. The result as before will lead to an eigenfunction f2x satisfying the following conditions. Namely, f2x is equal to lambda 2 integral a to b of k1 function of x and y into f2 which is function of y integrated over dy with lambda 2 greater than 0. Rewriting this, we have f2x is equal to lambda 2 integral a to b of k1 into f2 y minus lambda 2 by lambda 1 f1x multiplied by the integral of the product of f2y and f1y over dy from a to b. Now we multiply this equation by f1x and integrate over x. Then the left hand side becomes the integral of the product of two functions f1 and f2 over dx from a to b. The right hand side, the first term is lambda 2 and integral from a to b of f1x dx multiplied by the integral from a to b of k into f2y dy minus lambda 2 by lambda 1 integral from a to b of f1 square x dx multiplied by the integral of f1y f2y over dy from a to b. Using the fact that f1x is normalized, this last equation now reads 1 plus lambda 2 by lambda 1 within bracket multiplied by the integral a to b of f1x, f2x is equal to lambda 2 times the integral of f2y dy from a to b multiplied by the integral of the product of k and f1x dx from a to b, which in turn is equal to lambda 1 by lambda 2 integral a to b of the product of functions f1 and f2, both functions of y, and integral is done over dy. Hence, from this we can see that the integral of f1x, f2x dx from a to b is equal to 0. That is, f1 and f2 are orthogonal. We use this orthogonality of f1x with f2x to prove that the integral of k times f2y dy from a to b is equal to integral from a to b of k1 into f2y dy plus 1 upon lambda 1 integral a to b of the product of f1x, f1y, f2y dy. This can be seen to be equal to the integral from a to b of k1 into f2y dy. This is done by using the orthonormality, which is equal to 1 upon lambda 2 f2x from the equation 10.7 earlier. Thus, 1 by lambda 2 is the value of the integral I with f is equal to f2. Since the maximum value of I was reached for f is equal to f1, we have the result that 1 by lambda 2 is less than 1 by lambda 1. Thus, f2x is an eigenfunction of the kernel k, function of x and y, with eigenvalues lambda 2 greater than lambda 1. We can continue similarly by working with the kernel now k2 xy minus kxy minus 1 upon lambda 1 f1x f1y minus 1 upon lambda 2 f2x f2y. Provided the kernel which we have defined k2xy remains a positive kernel, we can proceed exactly as we did for k1. We look for the maximum value of the integral, say I3, defined as integral from a to b of this kernel k2 multiplied by the product of the function f at x and y into dx dy. This is to be maximized subject to the constraint that f is normalized, that is a to b f square x dx is equal to 1, that f and f1 are orthogonal, that is a to b fx f1x dx is equal to 0, and further fx is also orthogonal to f2, that is integral a to b fx f2x dx is equal to 0. As before, we call the maximum value of I subject to these constraints as lambda 3. Since lambda 2 is the maximum value of I with lesser constraints, obviously lambda 2 is less than or equal to lambda 3. So as earlier, we maximize now I3, which is defined as a two-dimensional integral over dx dy from a to b of the integrand k2, which is a function of x and y multiplied by the f of x multiplied by f of y. So we maximize this with respect to the variation in fx subject to the constraints. As in the last case, the solution is 1 upon lambda 2 f3x is equal to the integral over dy from a to b of the product of the kernel k2 and the function f3. Now we substitute for the kernel. So we get 1 upon lambda 2 f3 is equal to the integral a to b of the kernel kxy multiplied by f3y minus 1 upon lambda 1 integral a to b of the product of functions f1x, f2y dy minus 1 upon lambda 2 integral a to b f2x, f3y dy. Multiplying both sides by f1x and integrating over x, then we have 1 by lambda 3 integral a to b f3x, f1x is equal to integral a to b over dx and integral a to b over dy of the integrand kxy, f2y, f1x minus 1 upon lambda 1 integral a to b f1 square x dx multiplied with integral a to b or the product of functions f2y, f3y or dy from a to b minus 1 upon lambda 2 integral a to b of f1x, f2x over dx multiplied by the integral a to b of f2y, f3y over dy. Now this last term on the right hand side becomes, on reversing the order of the integration and the fact that kxy is equal to kyx, it becomes 1 upon lambda 1 integral a to b f3y f1y dy. The third term on the right hand side vanishes since f1x and f2x are orthogonal. Hence, we find that f1 is also orthogonal to f3, namely an integral a to b of f3x f1x dx is equal to 0. Similarly, multiplying equation 10.18 on both sides by f2x and integrating, we get 1 upon lambda 3 integral from a to b of f2x f3x dx, which is equal to 1 upon lambda 2 integral a to b of f2y f3y dy, and 1 upon lambda 2 integral a to b of f2 square dx multiplied by the integral from a to b of the product of the function f2 f3 over dy. So this is equal to 0. Hence, equation becomes 1 upon lambda 3 f3x is equal to the integral a to b of the kernel kxy into f3y dy, and by construction f3x is orthogonal to f2x and f1x, and lambda 1 is less than equal to lambda 2, which in turn is less than or equal to lambda 3. The process of defining new kernels in terms of the original kernel and the determined eigenfunctions, namely f1x, f2x, etc., can obviously be continued till such time that the integral forms I1, I2, I3, etc. continue to be positive. Now, let m be the lowest integer for which the integral Im defined as integral from a to b over dx and dy for x, both x and y have values from a to b. The integrand is kmxy fx fy, with kmxy given as the original kernel kxy minus sum over I from 1 to m lambda I fix fiy, where lambda I is the eigenvalue and when km is no longer positive. Summarizing, we have the following results when the integral I is positive. For such kernels, we have a sequence of eigenvalues lambda 1, lambda 2, lambda 3, etc. ordered in increasing sequence of the homogeneous Fredholm equation with a positive kernel. The sequence continues until a value mu m, which the kernel kmxy is equal to kxy minus sum I is equal to 1 to m fix fiy by lambda I is such that the bilinear integral I in equation 10.3 with k replaced by the above equation kmxy does not take on positive values. We now consider the arguments for negative values. If the integral I defined as I is equal to a two-dimensional integral over dx dy between the limits a to b of the kernel k function of x and y into a function of x and a function of y. So we define this two-dimensional integral over dx and dy where the integrand is the kernel multiplied by f of x and multiplied by f of y. And this is defined for any continuous and bounded functions f of x. We can follow, if fx is negative, we can follow an analogous procedure. We started with the first kernel km of x and y, which has become negative, and now minimize the value of the integral Im is equal to a to b over dx and a to b over dy, that is a two-dimensional integral dx dy of km function of x and y multiplied by f of x, f of y. That is km xy is the first kernel that becomes negative. So we minimize this with respect to variation in the function f of x. the results are totally parallel to the earlier case. All eigenvalues are now negative, starting with an eigenvalue lambda to the power minus 1. Repetitions of the construction of subsequent kernels, as in the earlier case, reveals the existence of a sequence of decreasing eigenvalues, that is, lambda minus 1 is greater than or equal to lambda minus 2 is greater than or equal to lambda minus 3, with associated eigenfunctions f of minus 1, x, f minus 2 of x, f minus 3 of x, so on and so forth. The orthogonality of these eigenfunctions with the ones for positive eigenfunctions is easily established. That is, our eigenvalues are lambda minus 1, lambda minus 2, lambda minus 3, lambda minus 4, etc. satisfying that lambda minus 1 is greater than or equal to lambda minus 2 is greater than or equal to lambda 3, and the corresponding eigenfunctions we designate as f minus 1x, f minus 2x, f minus 3x, and so on. So we have fn of x is equal to lambda n integral a to b of kxy into fny dy for positive eigenvalues lambda n, and for the negative eigenvalues we define f minus m of x is equal to lambda minus 1 integral a to b over dy kxy f of minus m dy. So we define the functions fn and f minus m for positive and negative eigenvalues. Multiplying the first equation by f minus nx and integrate over x, we get the integral of a to b fn x f minus mx dx is equal to lambda n, a two-dimensional integral for a to b over dx dy of kxy fny f minus m dx, which is equal to lambda n integral from a to b multiplied by integral a to b kxy fnx f minus my dx dy. On interchanging the order of integration and using the property kxy is equal to kyx, that is, kernel is symmetric. Similarly, multiplying earlier equation by fnx and integrating over x, we get the integral from a to b of f minus x fnx dx is equal to lambda minus m multiplied by a two-dimensional integral over dx dy of a and b, the integrand being kxy fnx f minus my. Subtracting this equation from the earlier equation, we get 1 upon lambda minus m minus 1 upon lambda n integral a to b of fnx f minus mx dx is equal to 0. Since lambda n is greater than 0, that is, the eigenvalue is positive and lambda minus m is negative, we have the orthogonality of the positive and negative eigenfunctions. Because for this to be 0, since lambda n can never be equal to lambda minus m, one is greater than 0 and the other is less than 0, so integral has to be 0, which establishes the orthogonality of the positive and negative eigenfunctions. If the sequence of eigenvalues is finite and is equal to n, this implies that the construction of kernel k1, k2, etc. stops at a certain point, and that beyond that point, the kernel kn plus 1 vanishes. Hence, in that case, it must be true that the kernel kxy is equal to the sum over I from 1 to n of the product of fix, fiy by lambda I is equal to 0. Thus, for a kernel with finite number of eigenvalues, the Hilbert-Schmidt kernel is degenerate. We will next prove that the procedure outlined above leads to the totality of eigenvalues. Now we are going to state a theorem. The theorem is that the eigenvalues obtained by successive extremization constitute totality of eigenvalues. There are no more eigenvalues which can not be obtained by this successive extremization. The proof of this is very involved, and in the first reading, if you wish, you can leave it. So let me indicate the proof. Let x be an eigenfunction with an eigenvalue sigma. Let f of x be an eigenfunction with an eigenvalue sigma, which we take to be positive. Identical theorem holds for negative sigma also. For simplicity, we assume that the successive eigenvalues lambda 1, lambda 2 lambda 3, etc. are non-degenerate, that they are all distinct, then since sigma is not equal to lambda I, we have from the orthonormality property of the eigenfunctions integral from a to b of chi of x fi of x dx is equal to 0, which means the function chi x is orthonormal to the function fi x. Consider now the integral I sigma, which is a two-dimensional integral over x and y. The limits are between a to b for both x and y. The integrand is kxy, chi of x, chi of y. As in the previous cases, the extremum value of I sigma is reached where chi satisfy the eigenvalue equation. Chi x is equal to sigma integral a to b k of x and y, chi y dy. And the extremum value of this integral I sigma is 1 by sigma integral a to b chi square x dx. Now, we had obtained the eigenfunctions fix and the eigenvalues lambda 1, lambda 2 by maximization of the integral I subject to a number of orthogonality conditions. Since chi is orthogonal to all the fi's at any nth stage of the successive maximization, we must have integral 1 upon b chi square x dx is less than or equal to the maximum value at any nth stage, which is less than or equal to 1 upon lambda to the power sigma. Thus, if there are infinite number of positive eigenvalues, we can go to n is equal to infinity limit, that is lambda n goes to infinity, in which case 1 upon lambda integral a to b chi square x dx is equal to 0, hence chi of x is equal to 0. If there are only a finite number r of eigenvalues lambda 1, lambda 2, lambda r, then we know that maximization of an integral like I sigma with chi x orthogonal to f1, f2, fr, etc. does not lead to a positive value, hence sigma cannot be positive. If sigma is negative, exactly the same chain of arguments, this time of minimization of integral I with functions fx obeying orthogonality properties lead to the final result as long as sigma is negative and chi is equal to 0. So as long as sigma is negative, chi is equal to 0. Having shown the sequence of eigenfunctions obtained is the complete set of eigenvalues and eigenfunctions, we prove an important result. What is the result? Result is that if p1x, p2x, etc. and t1x, t2, etc. are continuous functions which are bounded in their absolute value by some number mu, then in the limit n goes to infinity, the integral, that is the two-dimensional integral over x and y between the limits a to b of the integrand, which is kxy minus sum over I from 1 to n, or the product of function fix, fiy divided by lambda I multiplied by p and x, that this integral goes to 0. The result is a corollary actually of the result proved above. Say for positive lambda n plus 1 in the sequence of positive eigenvalues by maximizing the integral a to b over dx dy of kxy minus summation of the product of fix, fiy divided by lambda I, the whole thing multiplied by phi x, phi I, phi y. That is, instead of p n x, we have now phi x, phi y, and this is less than or equal to 1 upon lambda to the power lambda n plus 1 multiplied by the integral a to b of phi square x dx, and hence tends to 0 as n goes to infinity if the eigenvalues are infinite in number. Let us apply this last result for phi x is equal to p n x plus t n x. Now the integral a to b of p n plus t n whole square over dx is equal to integral from a to b of p n square over dx plus t n square over dx plus twice the integral of p n t n over dx. The first two integrals are bounded by mu. By Schwarz inequality, integral a to b dx p n x t n x is then less than or equal to integral a to b of Pn square dx under root multiplied by the under root of integral a to b dx Tn square x, and which is less than equal to some bound m. And hence the integral of Pnx plus Tnx whole square over dx is less than equal to 4m. Hence we have the result that the integral of kxy minus the sum over I from 1 to n of fx fy by lambda I, the whole thing multiplied by Pnx plus Tnx, further multiplied by Pny Tny, integrated over dx by and dy is less than or equal to 1 upon lambda n plus 2 into 4m, and it goes to 0 as n goes to infinity. But the two-dimensional integral over dx dy from a to b of the integrand kxy minus a summation over I from 1 to n of the product of functions lambda I fi of x fi of y divided by lambda I, and the whole thing multiplied by Pnx plus Tnx and further multiplied by Pny plus Tny. This integral is equal to the integral over dx and dy of the kernel kxy minus sum over I to 1 of the product of the functions f at x and y, that fix fy divided by lambda I, the whole thing multiplied by Pnx Pny plus Tnx Tny plus 2 Pnx Tny. The first two terms are bounded, each by mu by mod of lambda n plus 2, and goes to 0 as n goes to infinity. Hence the last term also goes to 0 as n goes to infinity. We'll find this result useful, and we'll find useful applications of this in the next unit dealing with the expansion theorem and inhomogeneous Fredholm equation. So students, let us summarize what we have learned in this module. We have seen that if f1x is an eigenfunction of the kernel k xy corresponding to the eigenvalue lambda 1, then there exists another eigenfunction f2 with the eigenvalue lambda 2 such that lambda 2 is greater than lambda 1. For such kernels, we have a sequence of eigenvalues lambda 1, lambda 2, lambda 3 ordered in increasing sequence of the homogeneous Fredholm equation with a positive kernel. The eigenvalues thus obtained by successive extremization constitute totality of eigenvalues. There are no more eigenvalues to be found. Thank you.